So this brings us to the last main topic, which may be split into a couple videos, but the last main topic of this first unit. So we're going to talk about least common multiples and what they mean, how to find them. So first thing, I'm just going to tell you, I'm going to abbreviate it a lot as LCM. So just get used to that abbreviation, least common multiple. So the first thing I'm going to have you do is look at these two numbers, 8 and 10. And what I want you to do, again, pause, come back to the video, is write or list the first 5 multiples of each. Okay, so pause and do that. So what I'm going to do is I'm going to write 8 first. So 8, it's basically counting by 8. 8, 16, 24, 32, and 40. Imagine on a number line, right? Jump counting by 8. 8, 16, 24, 32, and 40. And then for 10, it would be 10, 20, 30, 40, 50. Okay? So we've shown multiples for both 8 and 10. The first 5, we could go on forever. These lists could be infinite. So it's often helpful to find intersection points, right? Numbers that both lists have in common. So do you see any numbers that are multiples of both 8 and 10? Well, if we look at those lists, we see 40 in both lists. So then the question is, are there more? Well, if we kept going in our list, what you would find is that the next intersection point, the next common multiple would be 80. And after that, it would be 120. Every 40 numbers, 8 and 10 sort of converge. And so those are all common multiples. What we see here is the least of those, the smallest of those, the least common multiple. It might even be better illustrated if I use some smaller numbers, like let's say 2 and 3. We did this in a previous lesson when we were talking about prime numbers. We looked at how they had common multiples on a number line. So if I do the common multiples of 2, 4, 6, 8, 10, 12, 14. If I do 3s, it's 3, 6, 9, 12, 15, 18, 21. And you'll see that they have several things in common. They both have 6s in common. They both have 12s in common. If I kept going, this would go up to 16 and 18. And you'll see that they would both have 18s in common. So you keep running into common multiples. For our purposes, what we're looking at here are the smallest ones. The first ones in the list that they both have in common. So this is one way to find least common multiples. Just list them out and look at them. Find them. So now try the numbers 14 and 16. I'm sorry, 14 and 6. List the first 5 multiples of those. Pause the video, come back. For 14, this is a little trickier. You got to think about this a little harder. 14, 28, 42, 56, and 70. If I'm counting by 6s, it's 6, 12, 18, 24, and 30. So my question is, what's the least common multiple? We don't see it. There's nothing in those lists that they have in common. Does that mean they don't have a common multiple? No, any two numbers are going to intersect at some point. We just haven't gone far enough. The least common multiple is actually there already. We just don't know it's the least common multiple. We're usually going to get to it earlier in the list of the bigger numbers multiples. If I extend this 6 out a little bit further, you see we have 30, then 36, and then 42. So now you see the 42 is already here. Now you see it's also here. So there's that least common multiple. So the lists of multiples can be helpful, but they don't always work well. They're maybe not always the best or most efficient way. And one of the things we want you to get better at in math, algebra, is not just knowing a way to solve a particular problem, but having lots of ways. Life is all about problems, and you can't solve every problem the exact same way, even if it's a similar problem. Often you have to try different things. So I'm going to give you a different thing. Let's try these numbers. Let's try 27 and 36. Again, pause it, try it. 27 and 36. If we start listing out the multiples, boy, this is a little bit harder. I'd have to pull out a calculator to make sure I get these right, because in my head, once I get 27, 54, I believe 81 would be next. Now it starts to get even harder. I think we're at 108, and then I have to think even harder. 135. This is challenging to do in my head. 36 would be 36, 72, I promise you, I'm doing this in my head. Oh, actually, we ran into it there. 108. I can stop. Look at that. We did actually come to it relatively quickly. I can stop as soon as I find it. But that was hard, right? Looking at those numbers right away, I don't know if I might have made a mistake along the way, right? As I'm counting by 27s. So I'm going to give you an alternate method. What we're going to do is we are going to build the least common multiple, build the LCM. So this does take steps, and if you're a step person, you're going to like this. All right, we're going to build the LCMs, and if you remember to our conversation about prime numbers and prime factorizations, every number, every composite number, is composed of smaller prime numbers. And every number has its own unique prime factorization. And that's what we're going to use to build the LCM. We're going to use the prime factorizations of both numbers to sort of pull out pieces that they might have in common or might not have in common and build a bigger number. That's the LCM. So we're going to do the same problem. I'm going to do 27 and 36. And the first thing I'm going to do is find their prime factorizations. So 27 would be 3 times 9. 3 is prime. And then 9 is 3 times 3. So look at that. 27 is actually 3 times 3 times 3. Or we can write it as 3 cubed. And actually, when we're doing this particular method, this exponential notation works a little bit better. So then we go to 36. We did this one before. I'm going to do it as 4 times 9. 4 is 2 times 2. 9 is 3 times 3. Remember, we must always get down to prime numbers at the bottoms of our factor trees. This can be stated as 2 times 2 times 3 times 3, or 2 squared times 3 squared. And again, this is the notation that is going to be more helpful to us here. So now, what I'm going to do is I'm going to come down here and I'm going to rewrite these. 27 is equal to 3 to the third. 36 is equal to 2 to the second times 3 to the second. So, scroll up. To build the least common multiple, what we want to look at are these numbers, these prime factorizations. And what I'm going to ask you now are, what are the different bases that we have? What are the different bases, the factors, right, that you see in these lists? I see 2, I see 3, and I see 3. So the bases that we see are 2 and 3. Agreed? 2, 3, and 3. We see 2s and we see 3s. And then what I'm going to ask you is, what is the biggest power of each. So for the 2's, there's only one spot that the 2 shows up. And this 2 to the second power is the largest power of 2's. 2 to the second. What about the 3's? I've got a 3 here and I've got a 3 here. This is 2 to the second. This one is 2 to the third, and I want the bigger one. So the biggest power of 3 would be 3 to the third. Once we take the prime factorization and find the highest power of each factor, we just multiply those. We multiply those things together. We take 2 to the second times 3 to the third. 2 to the second is 4. 3 to the third is 3 times 3 times 3, which is 3, 9, 27. And 4 times 27 is 108. We took the components of 27 and 36. We found what they were made of. We found their ingredients. And we plucked the biggest parts that we needed and put them back together. And that gave us 108. There's a lot to follow there. Luckily, you have a video that you can go back to and watch. You can watch that example again, because we're going to do one final one. And this is actually going to involve 3 numbers. This would be really difficult to do without this method. 15, 28, and 98. We're going to find the smallest number that all 3 of those go into. Pause the video, maybe try it yourself. I'm going to keep going. Factor trees, prime factorizations first. 15 is 3 times 5. That's it. 28 is 4 times 7. 7's prime. 4 is 2 times 2. Those are both prime. 98, that's a tough one. It's 2 times 49. 2 is prime. 49 is not, but it's 7 times 7. Those are both prime. So now what we do is we take all 3 numbers. I like to stack them. 15 is equal to 3 times 5. 28 is equal to 2 times 2 times 7. I'm going to write it as 2 to the second times 7. And 98 is 2 times 7 times 7. So 2 times 7 squared. I'll scroll up so we can see it. So we just focus on these prime factorizations, right? The ingredients, the building blocks of each of those numbers. And we're going to pluck out every single factor, every single base. We need every single one of them. But we're only going to take the highest power of each one. So let's start with the smallest number. I see 2's. 2 here, 2 here. What's the highest power? It's the one with the higher exponent, 2 squared. I need that. I also see a 3. And I only see one single 3. So we just need one 3 in our least common multiple. I see a 5. I see a 5 right here, and I only see one of them. So we need a 5 in our least common multiple. And I see 7 a couple times. I see 7 here and here. Well, this one has the biggest power, 7 squared. So we need a 7 squared in our least common multiple. So notice how I did not have to use this 2 because this one already had a 2 in it. I didn't have to use this 7 because this one already had a 7 in it, right? It's like the squared were the bigger umbrella that fit all the other ones underneath. We didn't need to double up. We didn't need to add extra factors. That's how we end up with the least common multiple. Now we take all these things that we just found here and we multiply them together. So this will be 4 times 3 times 5 times 49. Pull up my calculator to do that. 4 times 3 times 5 times 49 equals, holy cow, it's a big number, 2,940. I don't think we could have come up with that if we had just listed out all the numbers. That would have taken up a lot of space. So again, least common multiples, the smallest number that all the numbers can divide into evenly. We can find it by making lists, or we can find it by building it using the prime factorizations.